Hello everyone. In this video, I'll be talking with you about the energy of an inductor, and it's a derivation of that energy function that we would usually find in a textbook, which is WL of t equals L over 2 times IL of t squared. IL of t is the current through the inductor, and WL of t is the work or energy of the inductor. And so we'll start our derivation of this formula here by taking notice of the fact that PL of t, which is power, is equal to dWL of t dt, which is also equal to VL of t I L of t. Now, for VL of t, we know that VL of t is L times the IL of t dt for any inductor. So we're going to substitute that over in here and then get an expression in terms of IL of t. So doing that, we have PL of t dWL of t dt equals L dIL of t dt IL of t. Then we have now is that we will multiply by dt throughout this whole entire three-way equation here. And so we have PL of t dt equals dWL of t, which equals L, and we bring the IL of t over to the front, IL of t dIL of t. Now, next what we'll do is we'll take notice of the fact that for power, with time, just in general, if we integrate this, then we get energy, which is just equal to work. And so we'll go ahead and impose that over here, and we'll apply integration here. So now we have integration of that, PL of t dt equals integration of dWL of t, which equals integration of L IL of t dIL of t. Next, what we'll do is we'll establish some integration limits here, and in order to do that, we will make substitutions using integration variables. So just any integration variable will do. Over here, I will use, in place of t, I'll use alpha. Over here, in place of WL of t, I'll use beta. And over here, in place of IL of t, I'll use just could be anything. I'll use a placeholder of A. And so now what we have is we have things freed up so that we can make the upper limit t, the lower limit t sub 0, PL of t, but now that's alpha, and we have d alpha there instead of dt, d alpha. And then next we have WL of t equals beta, so we have beta there, and d what? d WL of t. Actually, you don't have a beta there. We just have d beta, and then we'll put WL of t at the upper limit, WL of t sub 0 at the lower limit, and then we'll bring out L in front here, and in place of IL of t, we have A. In place of DIL of t, we have dA. Our upper limit will be IL of t. Our lower limit will be IL of t sub 0. And we'll carry on with our integration from that point on. So, free up some room here. And so now what we have, again, we'll restate this here, between t sub 0, PL of alpha, d alpha equals WL of t, upper limit, WL of t sub 0, lower limit, d beta is equal to L times upper limit of IL of t, lower limit of IL of t sub 0, A dA. And so next, what we'll do is we'll go ahead and we'll integrate. And in doing that, we'll keep this over here the same. So we'll just restate it. T sub 0, PL of alpha, D alpha equals beta to the first power over 1, which is just simply beta. So we have beta here, WL of t, WL of t sub 0. We have L over here, and we have A to the second power over 2. So now we have A to the second power over 2. And it's between the limits of IL of t and IL of t sub 0. Okay, so next, what we'll go ahead and do is evaluate the rest of what we have. T sub 0, PL of alpha, D alpha equals WL of t minus WL of t sub 0 equals L times IL of t, that's squared, over 2 minus IL of t sub 0, that's squared, over 2. So next we'll do is we'll go ahead and we'll apply the L in where we'll distribute it inward. We'll restate this over here, and so that gives us L times IL of t squared over 2 minus L IL of t sub 0, that's squared, and it's over 2. Now, WL of t sub 0, this is actually really the work of the inductor, the energy of the inductor with time. So if there's a initial condition, then you would include that in your evaluation of it. You would include this in your evaluation, and it would give you that. But in most cases, usually t sub 0 is 0. And besides that, what's more important is usually IL of t sub 0 is usually equal to 0, which just says that usually there's no initial current through the inductor. So we can simplify that even further, and we can just replace this with a 0. When we replace IL of t sub 0 with a 0, this whole entire term comes out. So when this term comes out, it corresponds to this term over here, WL of t sub 0. And then that comes out. So now finally we have between t and t sub 0, PL of alpha d alpha equals WL of t, which equals L over 2 times IL of t squared. And so that is our final result. So this shows the derivation of this famous formula that we have here for the energy of an inductor, the energy that it handles. It doesn't dissipate energy, not an ideal inductor at least, but now we have this derivation of this relationship here. So thank you for watching this video. Hopefully it was helpful, and have a nice day.